I shall brief you on another colligative property, that is osmotic pressure. Now you are familiar with the term colligative property. Colligative properties are those properties which depend only on the number of solute particles present in the solution and not on the nature of the solute particle. So these are properties which are the properties of dilute solutions. And we have got 4 types of colligative properties. They are lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. The first 3 colligative properties we have already discussed or have already briefed. Today we shall be moving on. In this video we shall discuss about osmotic pressure. Now we need to know, before we know what is osmotic pressure, we need to know what is osmosis. Now osmosis is a spontaneous movement of a solvent across a semi-permeable membrane from a less concentrated solution into a more concentrated solution. So this particular phenomenon, osmosis, happens when 2 solutions of different concentrations are separated by a semi-permeable membrane. Now what is a semi-permeable membrane? It's nothing but a membrane which allows only solvent molecules to pass through. It doesn't allow solute particles to pass through it. For example, the egg membrane, the cell membrane. Cell membrane is a very good example of a semi-permeable membrane. Alright, now we do have artificial semi-permeable membranes like deposition of copper ferrocyanide or calcium phosphate in porous materials, particularly porous pots. The porous pots, walls of the porous pots will be deposited by copper ferrocyanide or calcium phosphate. That becomes a semi-permeable membrane. Okay. Now it is this osmosis which results in the shrinking of say pickled mangoes and a shrinking of raisins, dry raisins. And when you put the dry raisins in water, it swells. That's because only water molecules enter the raisin by the process of osmosis. And when you put tender mangoes in brine or salt water, what happens? The solvent molecules in the mango will ooze out of it. Again, that's why the mango, the salted mango or the pickled mango appears in the shrunken form. So that is due to the phenomenon of osmosis. So our cell membrane is a very good example for natural semi-permeable membrane. And for synthetic semi-permeable membrane, you can quote the example of copper ferrocyanide deposited in porous spot walls or calcium phosphate deposited on porous spot walls. Now let us see here. Here you have a sugar solution on the left side of the picture. You have a container separated by a semi-permeable membrane, and on the left side you have sugar solution. Right side you have a solvent. And when you're separating these 2 solutions or these 2 different concentrations of solution by a semi-permeable membrane, you can see solvent molecules pass through the membrane and enter the sugar solution molecule. Sugar solution compartment. So ultimately, what happens? A lot of solvent molecules will come into the sugar solution side. And then finally an equilibrium will be reached wherein equal number of molecules of solvent will move to and fro between these 2 compartments. Alright, so this osmosis happens until an equilibrium is reached. Now that see here, when the equilibrium is reached, literally we feel that there is no osmosis happening. Though there is movement of semi-permeable membrane, movement of solvent molecules across the semi-permeable membrane, we feel that there is no movement because an equilibrium has been attained. Now, this this produced when this equilibrium is attained, what happens is an excess pressure is developed in the solution part. Okay, when a lot of solvent molecules move from the solvent side to the solution side, an excess pressure will be exerted on the solution side, and this prevents any more movement of the solid molecules. That's how it attains the equilibrium. So this excess pressure will prevent any more flow of the solid molecules into the solution side. Okay, and this pressure which prevents osmosis is called osmotic pressure. Okay, so when we separate solutions of two different concentrations, solid molecules from lower concentration will move into the higher concentration side, and when that happens, a pressure is developed at the solution side, higher concentration solution side, and this pressure will eventually prevent any more movement of solid molecules to it. This is how an equilibrium is attained. So this pressure which prevents osmosis is called osmotic pressure. Okay, so osmotic pressure can be defined as the minimum pressure that must be applied to solution side to stop the flow of solid molecules through a semi-permeable membrane. And it is a colligative property. It depends upon the concentration of solute particles in the solution. It is given by the expression pi is equal to mRT or CRT or nRT by V. Pi is a designation for osmotic pressure. Osmotic pressure is designated as pi. Okay, and here when the terms m is for the number of moles of solute particles per unit volume of solution. That is n by V is m, or some books say put it as capital C. Pi equal to CRT. Okay, n by V is m. R is the ideal gas constant and T is the absolute temperature. Now, how do we arrive at this particular expression for osmotic pressure? Now, that is derived from the laws of osmotic pressure. There are three laws of osmotic pressure: the Boyle-Van 't Hoff law, the Charles-Van 't Hoff law, and the Avogadro-Van 't Hoff law. Now, the Boyle-Van 't Hoff law states that at constant temperature, the osmotic pressure of a solution is directly proportional to its molar concentration. And it is given by pi is proportional to C, or pi is proportional to 1 by V. Now, Charles-Van 't Hoff law says that at a constant concentration, the osmotic pressure of a solution is directly proportional to its Kelvin temperature. That means it's directly proportional to temperature in Kelvin scale. And Avogadro-Van 't Hoff law states that, Charles-Van 't Hoff law is, the expression for Charles-Van 't Hoff law is pi is proportional. The Avogadro-Van 't Hoff law states that the equimolar solutions of different solutes at the same temperature exert the same osmotic pressure. That means different solutions of the same concentration will exert the same osmotic pressure. Such solutions which exert the same osmotic pressure are called isotonic solutions. Alright, so isotonic solutions are solutions of different solutes of the same concentration, and they exert the same osmotic pressure. Now, combining all these three laws, we have got the expression for osmotic pressure. Let's see how we derive this expression for osmotic pressure. Now, we have the Boyle-Van 't Hoff law, which says that pi is proportional to 1 by V, and the Charles-Van 't Hoff law, which says that pi is proportional to T. You combine equation 1 and 2, you get pi is proportional to T by V, and rearrange it, pi V is proportional to T, and you introduce the proportionality constant S, pi V is equal to St, where S is called the solution constant. Now, it's been found that S is similar to the gas constant. The value of S is almost same as the universal gas constant. So you can put it as pi V equal to RT also. Now when n moles of the solute are present in V volume, volume V, then we put it as PV equal to NST, and instead of S you can put it as R, the gas constant, so pi V equal to nRT. This is the Van 't Hoff equation for dilute solutions for osmotic pressure, or Van 't Hoff osmotic pressure equation. Now you rearrange this, you get pi is equal to N by V RT, or pi is equal to CRT, or pi is equal to MRT as we had written earlier. So pi V, you can, instead of you take this equation 8, can be rewritten as pi V equal to, instead of N you can read weight by molecular weight, that is W by MRT. Alright, so using this expression 10 you can calculate the molecular weight of the solute present. Okay, and so that is given by M, molecular weight of solute, equal to weight into RT by pi V. So if you know the osmotic pressure, you can calculate the molecular weight. So this is the expression for osmotic pressure and the relation between osmotic pressure and molecular weight of the solute. Alright, now how do we measure osmotic pressure? That is done by Berkeley and Hartley's method. It's a very simple method and quite an interesting method also. Now this is the apparatus for Berkeley-Hartley method. You find here there are two cylinders. See, this plain cylinder on which solution has been written, and into it, inside, there is another cylinder written as water. Okay, so they are two concentric cylindrical tubes. So the inner tube is porous tube. So the tube in which water is present is made up of semi-permeable membrane, particularly copper ferrocyanide. You can even have calcium phosphide. Okay, so this copper ferrocyanide membrane acts as a semi-permeable membrane, and you take pure water in it. All right, this tube is fitted with a capillary tube and a reservoir. All right, we'll know what is the use of this. Now this tube is the inner tube is put into another tube, that is another bronze tube, a bronze cylinder in which the solution is taken, and this bronze cylinder is fitted with an external pressure gauge. Okay, a piston and a pressure gauge. So you have the piston here, okay, and then that is connected to the pressure gauge. So the pressure gauge measures the pressure, and the piston is used to apply pressure externally. Alright, now this side tube, that is this capillary tube, is used to monitor any change in the pressure. Now how is that? The change in pressure can be monitored by the change in the water level in this capillary tube. So how does that happen? You are immersing this cylindrical tube or containing pure water in a tube containing solution. So by osmosis, what happens? The water molecules will pass from the inner tube to the outer tube. So when water molecules pass from inner tube to the outer tube, what happens? There will be a decrease in the capillary level, the level of water in the capillary tube. Okay, so that's what is written here. Water is kept in the porous cylinder while the bronze cylinder is filled with a solution whose osmotic pressure is to be measured. And when water is placed in the porous cylinder, it tends to pass into the solution through the semi-permeable membrane, and the capillary tube, the water level in the capillary tube moves downwards. An external pressure is then applied using the piston, so that the water level in the capillary tube is maintained. So when you apply an external pressure, what happens? The pressure is exerted on the semi-permeable membrane, and no solvent molecule will pass across the semi-permeable membrane. So that pressure which stops this movement of solvent molecule is measured using the pressure gauge, and that will be the osmotic pressure of the solution. So that's how the osmotic pressure is measured using Berkeley-Hartley method. Alright, so this applied pressure will be equal to the osmotic pressure of the solution. The advantages of Berkeley-Hartley's method of measurement of osmotic pressures are: it is a quick and accurate method, and this method can be used to measure high osmotic pressure because the osmotic pressure is balanced by external pressure, so there will not be any strain on the semi-permeable membrane, and so there will not be any damage to the membrane. Alright, and then this method, the pressure value, osmotic pressure value which has been obtained by this method is reliable because the concentration of the solution does not change because of the flow of the solvent is not permitted into the solution. Since the flow of solvent is not permitted into the solution, the concentration does not change. So these are the three advantages of measurement of osmotic pressure by Berkeley and Hartley's method. Now we need to know one more concept when we discuss about osmosis and osmotic pressure, and that is reverse osmosis. Now reverse osmosis, as the name suggests, is the reverse of the osmosis. So that means in osmosis, solvent molecule move from lower concentration site to higher concentration area. Right? So the reverse of it will be the solvent molecule will move from high concentration solution to low concentration solution. So it is a process of forcing a solvent from a region of high solute concentration through semi-permeable membrane to a region of low solute concentration by applying a pressure. So remember, osmosis is a spontaneous process. You need not apply pressure on it. But reverse osmosis is a non-spontaneous process. You have to apply an external pressure for the reverse osmosis to happen, because it is against the natural tendency. Alright, so we can depict the reverse osmosis in this way. You have the salt water on one side, fresh water on the other side. So you apply pressure on the salt water side, so the water molecules will move through the semi-permeable membrane to the freshwater side. Now this reverse osmosis phenomenon is used to purify water, to desalinate water, etc. That comes under the applications of reverse osmosis. So coming to the applications of reverse osmosis, one application is desalination of seawater. So here you have on one side you take the seawater, you take a tank, make it into two compartments using a semi-permeable membrane, and then on one side of the in one compartment you take the salt water, and in the other you take fresh water. You apply pressure on the salt water side. What will happen? Only water molecules will move from salt water to freshwater side, and all the other salt particles and other pollutants or other minerals present in seawater will be left behind, and only water molecules, pure water, will pass through. So this is particularly used in Middle East countries to make to get fresh water. Their fresh water is not abundant, so they go for desalination of seawater. Alright, so you apply a pressure on the solution side or seawater side, and reverse osmosis will happen. So this membrane for desalination of seawater, special membrane, the semi-permeable membrane, is made from nylon or cellulose acetate, etc., which can withstand very high pressure. So this fresh water which is obtained by desalination can be used for drinking purpose. Another application is for the production of bottled mineral water, and also in household water purifiers. They are also to purify water and to remove dissolved salt and other impurities present in water. We can go for reverse osmosis phenomena. This will filter off or separate all the dissolved salt, minerals, particles, dyes, etc. So purification of polluted water is also possible. And when you use the water purifiers, when you apply, these water purifiers When you pass through the water through the semi-permeable membrane, and the water which you get out of the water purifier will be pure water. And another application is for the wastewater purification. The same way what we have done for desalination, the same methodology can be used for purification of wastewater. So industrial wastewater effluents can be purified and let off into the environment after treating it through the tank having a semi-permeable membrane. And then in food industry also, reverse osmosis is used, particularly for concentrating food liquids, liquid foods like milk and fruit juices. And this is easy because you're not applying any heat. So usually in order to condense liquid food, we apply heat and evaporate the water content. But here you can carry out reverse osmosis and remove the water content. So heat sensitive materials like proteins and enzymes will not be affected. So we use this particularly in dairy industry, that is in milk industry, for the production of milk powder. Then wine industry, juice industry, etc. we go for the reverse osmosis method. So that's about osmotic pressure, reverse osmosis, determination of osmotic pressure, etc. Hope it's clear to you. Thank you.